Am I audible? So good evening. My name is Kevin and I'm from PeerDB. And today I'm going to be talking about how we at PeerDB are building a data movement tool specialized for Postgres. So today's agenda, so we'll begin by going over an overview of PeerDB. We'll talk about the use cases of such a tool, the terminology that we use, and some of our types of mirrors. We'll also talk about how we are building PeerDB, like what is our architecture and our component choices. Then we'll go through some of our Postgres-specific optimizations, and I would prefer questions at the end of the presentation or when I specifically ask for them. So what is PeerDB? So we at PeerDB are a Y Combinator startup that is aiming to build a data movement / ETL tool focusing on moving data from Postgres to a few destinations. The reason we are building PeerDB is we have realized that a lot of existing tools in this domain either they don't hit some performance requirements, like they are little too much latency, or they don't support some Postgres features like say partition tables or PostGIS or headstore, some extension. And so we want to sort of fill that niche. So we aim to be a great ETL tool, but also support all the features of the Postgres ecosystem and stay relevant with feature additions like new extensions or new features added to Postgres as versions increase. So these are our supported destinations. So our only source is Postgres, but we move from Postgres to 3 primary types of destinations. So the first class is data warehouse. So that would be Snowflake or BigQuery right now. These are like all app stores which are really built for analytical queries, so for analytics report generation. The second and third type are message queues. So right now we support Azure Event Hubs, and we also plan to add support for Kafka. And the third type is object storage. So right now we support Google Cloud Storage and Amazon S3. But we primarily focus on the data warehouses because that's the more 1:1 sort of table mapping thing. And just a quick, a quick intro to myself. So I, unlike a lot of speakers here, so I graduated from college around 3-4 months ago, and PeerDB is my first job out of college. And I've learned a lot in the past few months working on Postgres and other databases, and I'm excited to share some of the knowledge I have acquired over the past few months. So we'll talk about PeerDB's terminology. So a peer is what we refer to as a data store. It could be a Postgres database or a Snowflake database or like a Event Hubs namespace. And a mirror is a connection between a source and a target peer. So it could be a Postgres to Snowflake connection or a Postgres to Event Hubs connection. So a peer is an abstraction over a data store, and a mirror is a connection of some type between the source and a target peer. And the way we interact with all this is a UI or an SQL interface, which we'll get into later. So we'll get into 2 types of mirrors we have. So the first type is write-ahead log or CDC-based replication. So this uses Postgres' logical replication capabilities. How many here are familiar with how logical replication works? Okay, so not me. Okay, so basically we use Postgres logical replication capabilities. This is a mechanism that Postgres has that basically streams changes to a table in near real time. So with these types of mirrors, we can stream inserts, updates, deletes from the selected tables to the destination in near real time. We handle those columns, and we also support adding some sort of schema changes. So in case a column is added on the source, we automatically replicate it to the target table within a few minutes. So this is a single sort of mirror which has 2 phases. We first move existing data from the source to the destination. So there's a first phase where we sort of snapshot the initial tables. And then after the initial snapshot is done, we start streaming the val continuously. And we sort of read events in batches and push them to the target database. So this is also, we make it as efficient as possible. So we first of all start streaming the val. So Postgres, we read the write-ahead log, we read the changes that have happened. We read and push events in parallel. So Snowflake or BigQuery, for example, data warehouses, we have a raw table where you push the events to the raw table, he puts them in an optimized manner. So we send like a batch of 100,000 events or 1 million events all at once to the table, using either Postgres' binary copy or BigQuery's. We use Avro or like we use a compressed format to send the rows as fast as possible. And then after we get the events, to reconcile them to the final tables, we use a single statement merge. So we have a single merge statement that sort of handles inserting, updating, and deleting rows to the final table. So this is essentially a very optimized pipeline for moving rows from a source Postgres table to a target Snowflake or BigQuery table. So the advantages of such an approach is it's optimized for continuous replication. So Postgres logical replication is the way Postgres does, it does data replication to subscriber, and this has low overhead as a result because it's sort of built for the thing. The second thing is it has an ability to stream delete. So deleted rows can be replicated to the target easily. And the third thing is the table can have any schema as long as the primary key is present. So the primary key is a requirement. The disadvantage of this is the table needs a primary key. So the way logical replication works for most cases, we need a primary key to do the logical replication. There's something called replica identity full. When you set the replica identity for a table, you're essentially asking a Postgres to treat the entire row as a primary key, which obviously is not ideal for a lot of cases, and it kind of kills performance in some cases. Logical replication needs to be supported by the providers. So most providers, AWS, Cloud SQL, all of them support logical replication, but I think Heroku does not. So it's not a given that logical replication is supported for your cloud provider. The third thing is replication slot management is a tricky business. So as you're reading the changes from the database, there's a lot of things that could affect it. Earlier talks got into how a long-running transaction or a large load could get and make the replication slot size sort of explode, and that can sort of kill performance for a while. And the fourth thing is the reading of the slot is a single thread operation. You can only have one subscriber to a replication slot at a time, and this operation is a single thread, which could be a bit slow. The second type of mirror we have is a query replication mirror. So this is a much more sort of like intuitive approach. We just stream the results of an SQL query to on Postgres to any of our destinations. And this opens up the possibility of any transform. So we could do a select star or a select, we could do a join between two tables, or we could even sort of rename columns on the fly and do transformations on the data as we read it. And this result set of the query is pushed to the destination. The only requirement is we need a cursor. So we need a cursor or watermark column to sort of refer to older and newer rows and sort of distinguish between them. So it could be an ID of a row or an updated add column. And this is basically the way we can distinguish between older and newer rows. And every time the mirror reads this, it kind of can see the newer rows have been added and pushes those newer rows to the destination. The result set can be run in parallel. So since this is basically a SQL query, we can read them in parallel. We can use parallel cursors and sort of split the query into multiple sets to be read in parallel. By default, we only append rows, so we can't do any updates or deletes by default. We can do an upsert by choosing a unique key of the table as well as a watermark. So the unique key is sort of distinguishing between old and basically like the ID of a row. And the watermark is saying if the row has been touched or updated. Deletes are unsupported. So with this mode of replication, we can't tell if a delete has happened. So because we're just reading the results, we can't tell what has been lost from this. And again, we make this as efficient as possible. We batch all the rows we get and send them to the destination in a single step using copy. So the advantages of this are we can use it without a primary key. So in case a table does not have a primary key, this can be used in that case. We can do complex transforms. So we can do a join on a 2-3 tables. We could basically transform it and make it do the transformation and load at the same time. And this is parallelizable. So we can sort of configure how many threads you want to read the result set with, and you can sort of scale it up or down based on the database and requirements. The disadvantages of this are you can't replicate deleted rows without a full table refresh. As I explained earlier, you can't replicate deleted rows until you read the entire result set again and sort of reconcile the changes. And you need to have a watermark / cursor column. So if you can't have a cursor that's meaningful in your result set, you can't really use this method of replication. And the way we decide between the two means is based on the customer's requirements for latency and whether need deletes, and we sort of set it up for the customer based on what their requirements are. So now we'll get into the, before any questions, before the next section. No questions? So we'll get into the next part of the presentation. We'll talk about how we are building PeerDB. So this is our architecture. I thought I could present better, but this is not barely. Okay, I'll try my best. So the way users interact with PeerDB is through two means. So we have our UI, which is basically a web browser UI, which is pretty typical for a lot of the tools in the thing. We just have a web interface to create a peer, set up a peer, and then set up a mirror, and sort of monitor the status of the mirror as well. And the second way is through a query layer. So this is sort of a unique feature we have. So you can sort of connect to PeerDB as well as a Postgres instance. You can connect to it via PSQL or any of your Postgres existing toolkit. And you can query the peers to some extent with it. So you can, if you had a BigQuery or a Snowflake peer, you can query the BigQuery or Snowflake peer as if it was a Postgres peer. We sort of rewrite the query for sending it to the BigQuery or Snowflake. Along with this, we have added custom SQL commands. So we have added SQL commands to sort of create a peer, create a mirror programmatically. And this is very useful for data engineers because they can use an existing infra to sort of create 100 mirrors instead of going to the UI for each mirror. And this is the query layer. So these are two ways users can interact with PeerDB. The next, after all the requests for creating a peer or a mirror is sent to the Flow API server. So this API server is what sort of responds to requests and mirror creation requests and sort of manages the state of a mirror. And after that, the actual work of the mirror, actual reading and writing data is done by a set of flow workers. So we have a lot of flow workers now. It could be one flow worker or 100 flow workers. It's all horizontally scalable. So the orchestration between the flow workers. So the Flow API sort of sets up the mirror. But the orchestration of the mirror is done by a sort of system called Temporal. This is a workflow orchestration engine. Basically, we split up a mirror into a set of activities. We have setting up our tables, we have setting up the replication slot. All those activities are run by Temporal on an available flow worker. And this has an advantage in case the activity fails. For example, I couldn't create a table. Temporal automatically detect the failure and retry the activity. So our mirror is basically rock solid. It will either fail and then retry itself, or it will essentially report that it has failed and can't proceed from now on. And then, like the flow workers read from our Postgres and can write to any of our supported destinations. And finally, we log statistics and all our mirror configuration, all our basically data in a Postgres instance, obviously. So our catalog is where we store all the Postgres data, and there's a Postgres database you can query and you can run statistics against yourself. It's exposed to the end user. So this is just an example of a query layer. So you can see that we have added custom commands to sort of create a Postgres peer, create a Snowflake peer. It sort of validates the connections and returns to the interface. And now this you can set up a mirror saying, remove this table, these two tables from the source to the destination peer. And after it sets up the mirror, it automatically starts replicating data after the mirror setup. So this is basically a command line interface to an ETL tool, and you can also get feedback in terms of statistics by just running queries against stats tables that we expose in the same interface. Yeah. Okay, so before we move to the next, the final part, are there any questions? So we'll move on to the last, we'll talk about some of the features or optimization we have for the Postgres ecosystem. So the first one is schema changes in CDC mirrors. So logical application is really powerful. Okay, so logical application, are people familiar with how it works? Okay, so I'll just give a brief overview of how logical application works. So we have three primary components for logical application. We have a replication slot, a publisher, and a subscriber. A publication and a subscriber. So the replication slot is basically a channel to which you can read the val. The replication slot sort of maintains at what point on the val it is, the write-ahead log. A publication. So I can just ask a publication to show me the changes for the schema or this table or even columns. So publication can actually filter on a column level as well. So a replication slot is what sort of sends the messages a subscriber is what connects to the application, is what it tells it I've read till this point and I can continue reading from here. And the publication is what you use a filter. The filtering is done by publication. You can filter on table, column, or schema level using a publication. So we'll just move on. So logical replication has a limitation in which it doesn't send detailed command information over to the subscriber. What that means is it tells me when I've inserted a row or deleted a row or updated a row, but it doesn't tell me when I've done a create table or alter table command. So it doesn't tell me whether the table schema has changed directly. But what we instead get is something called a relation message. A relation message is basically a message that says this is the table, these are what columns it has, and this is what Postgres sends to us so we can decode other message, right? So, for example, a table has 4 columns. You get a relation message saying column 1, type 1, column 2, type 2, so on. And then we get an insert message that tells that a row has been inserted and what data it contains. You have to use the relation message to decode this insert message. So this is what it sends. But the thing is, when it changes schema, we need to send a new relation message. Because if I've added a column to a table, we need to obviously know that the column has been added. So what we get is a new relation message that sort of tells a new column has been added or the old column has been dropped. And we can sort of store the old relation message, see the new relation message, and compare the two and just see that this column is gone or this column has been added. And by just reading the relation messages, we can sort of apply the delta that you have seen. We can add the new table to add the new column to the destination, or add the new column to drop a column from the destination. So we are just using existing capabilities of the Postgres logic replication protocol to do basic schema changes. So we can't do complex ones. We can't figure out when a column has been renamed because we can't tell what was renamed to what when it's looking at before and after. But we're able to get them to a large extent. So there's a complication to this. We'll just get into this. It's very interesting. So look at these set of 8 commands over here. So we create a table, then insert a row. Then we have a transaction where we add 2 columns and then add 2 rows between the 2 columns. So what we are supposed to do is, like, if you have a destination table, if you're replicating this to BigQuery or Snowflake, by the time we read this insert, we need to have this column C3 added to the destination, because the default value basically indicates that this row needs to have 26 in column C3. So by the time this is replicated in the final table on the destination, we need to have this column C3 set. So what we could do is we could read till this alter, detect the relation message of the alter, then stop reading the value. You can indicate to Postgres that I'm stopping reading here, I'll resume later. Then go to BigQuery, add column C3, and then get back to reading the val and read the second alter column, read this insert and proceed. But in practice, what ends up happening is if I stop in the middle of a transaction and I start resuming, it will start when the transaction is beginning again, because the way logical replication works is that even if I'm reading committed info, so this is logical replication only gives you things that are committed. It doesn't give you in progress sort of changes. But even though it's already committed, it only lets you read from the beginning to the end of a transaction. So if you stop in the middle, you'll get the alter table again and see the same change again, and this will sort of repeat itself. So the way we actually do it in practice is we have to read the entire transaction there. So a transaction could have 1 million rows or any amount of rows, but you read from the beginning to the commit and sort of stage all the changes. So in this case, what you'll have to do is add C3 and C4 at the same time to the destination. After we add C3 and C4, we can add the insert. So it's doing it out of order. We are doing the changes out of order, and then after that moving the rows to the destination table. The second thing is how we do a parallel initial snapshot. So like I discussed with CDC mirrors, we need to move initial data over to the table, to the destination table, before we start continuous replication. But this has to be done really fast could be hundreds of tables. So we could be reading terabytes of data in the initial snapshot to move over to the destination. So how we end up doing it is, so Postgres has a feature called snapshots. Snapshots of how Postgres implements transaction isolation. So if you start a transaction at either repeatability to serializable levels, a transaction has a snapshot of the database it's seeing, and the snapshot is an identifier. So it's like human readable identifier. What we can do is, suppose a transaction started 20 hours ago, like a long-running transaction. I can use the same snapshot of this old transaction, set it into a new transaction, and I can have the new transaction have the exact same view that the old transaction has. So this is a way of sort of sharing views of different transactions. Now the application slot can also export a snapshot. So the application slot, when you create an application slot on Postgres, it exports a snapshot which we can use as long as the application connection is held. So we'll just get into how we do this. So we have a snapshot connection open. So this connection is what we use to create the application slot, and we hold it open until the initial load is finished. So we have a snapshot that is used for the initial load. Obviously this is a long run transaction, so it kind of has some issues, but this is how we do it. So after we have the snapshot connection held, we can then read a table, and again you can read it in parallel. Like I explained in the query application, we could sort of see, I can do select count star of my table, get 1 million rows in the table. And then after I know I have 1 million rows, I can start 5 parallel threads that read from 0 to 200 million, 200 million to 400 million, so on, using like where queries. And I can have 5 cursors operating in parallel, reading the same table and moving it parallelly to the destination. And after it's moved to the destination, we just have a single copy to the final table. So again, like here we are parallelizing a table read and also parallelizing across tables. So I can have 4 tables being moved in parallel and 5 threads per table. And sometimes instead of using an index, we switch to using a CTID instead. So CTID is a system call, just like Xmin. So instead of integrating transaction ID, the CTID is basically a way of saying, representing a disposition of a row. So CTID, if 2 rows have a similar CTID, it is basically saying that the 2 rows are close by in the physical disk. So now if you're reading all the rows, sometimes it is more efficient to read them via CTID instead of the actual index of the table, because CTID is a physical location. Like the disk file contains these many rows because and all are in the same area, so the I/O performance is slightly higher because, as Shailesh had explained earlier, Postgres rows are immutable. So when I update the row, the updated row might be completely different page or completely different physical location. So by reading by CTID, we get the performance because you're reading all the rows that are together in the same I/O location, and sort of makes it even faster. And with this, you can move a terabyte plus of Postgres tables in under 12 hours, and this sort of makes an initial snapshot take hours instead of days in most of our customers. So we'll also talk about how we support partition tables. So partition tables are a very common thing to use for large tables, especially time series data. Extensions like pgpartment are very common for automatically creating and dropping partitions, because like pruning data. But the thing, and replicating partition tables to data warehouses is a very common use case, because you want an analytics against the destination, against the data. But this needs to account for adding partitions, dropping partitions dynamically. So in Postgres 13 plus, partitions actually support this option that sort of rewrites the logical application message to refer to the parent table. So how partition tables actually work is, we have a parent table which is a virtual table, and a lot of child tables which actually store the data, and the parent table is just a reference to the child tables. So in Postgres 13 and above, we can use this option to sort of make the replication message seem like it's from the parent table. In Postgres 12, this option isn't there. But since we want to support older versions of Postgres, what we end up doing is looking at the child partitions ourselves. So we can see, using some catalog query, that this table has 100 partitions. And every time we see one of these 100 partitions, what we end up doing is rewrite the message ourselves to point to the parent table and then proceed. So in case you get child table 117 or something, we just rewrite it to point to parent table and then proceed with the logical application. So last feature I talked about is how we added Postgres support. So Postgres is a very, very popular Postgres extension that adds custom geography and geometry types. So we read this on Postgres in a format known as WKB, well-known binary format. And what we end up using is a library called libgeos. Libgeos is the same library that Postgres uses. So we use the exact same library that Postgres itself uses for its geometry and geography support to pass and validate the data, and then we convert it to another format called WKT format. The advantage of this conversion is in case the database supports, Snowflake supports geography for example, we can just convert this WKD to the geography type of Snowflake. But in case the destination does not support this geography data types, instead of just giving it an opaque identifier, like a binary thing, we convert it to a human readable text format before sending it to the destination. So we get the best of both worlds. We can have either native support for geometry types, or we can convert it to a string so other destinations can also see the data in human readable. So we'll, in summary, some of our optimizations are, we have transparently added a way to add new columns to the destination tables to prevent any data loss during the replication phase. We have a parallel initial snapshot to reduce mirror setup time from days to hours, improving the database health during the snapshot process. We have support for partition tables, which is a very critical ecosystem feature, and we support it even for old Postgres versions. And finally, we support Postgres along with some other extensions of the Postgres community. And this is part of a commitment to supporting a lot of the features that Postgres has that are not part of the base database. Some of the future optimizations we plan to investigate and maybe implement is, so logical application is a protocol. It has it's a protocol where you get messages of a certain type, and over time this logical application protocol has had new versions. It's like a V2 of an API, a V3 of an API. So in Postgres 16 there's a V4 of the protocol, and the newer protocols have added support for streaming in progress transactions. So I just mentioned how the initial implementation of logical application would only replicate a transaction after it's been committed. But obviously in case of a large transaction, that is not ideal. So in case a transaction is running for say 5 days for example, only after it commits I will get the 10 million changes that the transaction did, and that can immediately sort of hamper the reading of the val, because now PeerDB and Postgres both have to decode the changes that has been just committed. So it has to sort of handle all of this. And send the entire transaction changes at once, and this can sort of slow down logical application a lot. And with this newer feature of the protocol, we can stream in-progress transactions. So we can stream the transaction as it happens, and then the end, Postgres tells us whether it committed or aborted. And then we can use the rollback or the commit to either discard the changes we received from the slot, or we can commit them to the destination as per usual. This also adds support for two-phase commit. So this is added recently as well in the protocol. So two-phase commit is sort of prepare transaction. I'm not sure if that's very commonly used, but yeah. We also plan to write extensions for either having raw data access to the underlying Postgres data files, and also for making CDC messages more efficient or making it convey more data. So as we are a Postgres first ETL tool, and we want to sort of invest all we can into making the reading from Postgres as efficient and as reduced latency as possible. So we are on GitHub, so we are developed in the open, and you can try this out in like 5 minutes. We have a Docker compose that we use. So you can try it with our sources and destinations. We support Postgres as destination as well, so you can just go Postgres to Postgres and see if it works. And we have a public Slack channel, so we can just either hit us up in case it's an issue, or maybe contact us, and maybe even contribute, who knows. So thank you. This is our GitHub link, and you can reach me at this email address. So that's pretty much it. Thank you. Are there any questions, Archie?
Quick question. Good. So I'll ask. You said that about the very long-running transactions.
Yeah.
And PeerDB is actually developing the CDC tool to accommodate those changes, right? So I'm curious to know, what are the use cases where you said that there could be a 5-day long transaction?
That was a bit of a exaggeration, but there are cases we've seen in some of our customers where there's a long-running transaction of some kind, and after the transaction is committed, we get a bunch of changes at once. And what happens is that sort of makes the val decoder take a long time to process the entire transaction at once. It's not a common thing. Obviously, long-term transactions are not a common practice, but we have seen cases where our reading of the slot is hampered because of a long-run transaction, and this change that Postgres has made from its side, it will help us with those cases.
So what are the versions of Postgres you are supporting?
So yeah, I think
No, peers. Good.
for peers or like
For peers.
no, I didn't answer that
For
question.
peers. No, say for example, if I have a Postgres 10 version,
Yeah.
do you guys have the supportability of the PGDG or you can go back?
Okay, that's a good question. So I'm not sure what the exact version of Postgres support is. So we have added support for features that Postgres 12 lakhs or Postgres 11 lakhs. But in general, it's more of like if it works, if it doesn't work, you can sort of reach out and then we can get it working. Because it's primarily based on like what a customer or a user sees. If a user has an issue with some feature that doesn't work in Postgres 10, we can sort of see and sort of implement it. But yeah, there's no, I don't think it's a firm version. I don't think I've seen a Postgres 10 user yet. But it could be possible. I can get back to you later. Any other questions?
So, are you ensuring that transactions are atomic even in PeerDB as well?
Atomic?
So, you mentioned that you're doing out of order schema change reads, and then there might be some insertions which can also happen within the transaction. So, I don't see how PeerDB is actually replicating that entire atomicity. Does temporal handle it or?
No, so that so basically we add column C3 and column C4. We do that in the first step. Now the first row did not refer to C4 ever. The first row just talked about C1, C2, C3. When the first insert was processed by Postgres, it didn't know C4 existed. The second column existed. So the first insert message does not actually refer to C4. So when we add it in a destination table, C4 just ends up as none.
Yeah, so my question is basically, you're not looking at the transaction, you're looking at the logs of it, right?
You look at the logs of transaction.
But when you're doing the replication and say in between it fails, as a transaction you're supposed to roll back to the state it was before the transaction. But is PeerDB also going to do that for the target? How does
The
it
target, so we do our merge statement. So all the changes are done in one statement. So that is rollbackable. But currently we apply the schema changes in a different phase. So the schema changes are applied before we start moving the rows to the table. So there could be a state where we have added the columns but not moved rows matching the columns. But if we are moving it, we'll move it all at once. Like the transaction is moving the rows to the table, but the adding columns is in a different phase of the grid.
Yeah, so that's what I felt like you're breaking those things into two.
Yeah, we are breaking it into
It's
two.
still atomic.
Right now it's not atomic.
Yeah, that's
It's
what.
not atomic.
Yeah, you should make it atomic, right?
I mean it depends. Like what are the use cases of it being atomic?
It's a transaction in Postgres. It should ideally be order is fine, but he's I don't think he's maintaining the atomicity of that. So just look at
No, you're basically saying that
But
in
I
case the inserts don't happen, the schema changes also not happen in the target level.
Yeah.
Okay, makes sense. Yeah, right now we don't do that.
But I think you mentioned in the end you're working on this new logical replication.
Yeah, we're working on a thing where a large transaction can be streamed in that phase. But right now that's not there. So what we do is we are completely it's not atomic in that sense. Schema changes are applied in a different phase than the moving of the rows. I'm not sure that actually is that could be an issue in some cases, but you're not seeing any issues with the way we do it yet. But yeah, it's not atomic at the moment. That's correct.
Thank you so much.